This video lecture is talking about the end of buffers and buffer capacity. I wanted to talk about a little bit more about buffers and using the Henderson-Hasselbalch equation to try to calculate buffers and how to make a buffer, and then also how do you figure out changes in pH when you add a strong acid or strong base to a buffer. The first thing we're going to look at is A up here, about an example about calculating the moles that you would need to add of a particular base or acid to figure out a certain pH for the buffer. So how many moles of NH4Cl must be added to 2.0 liters of 0.10 molar NH3 to form a buffer whose pH is 9.00? One big assumption here at the beginning is this, you're not changing any of the volumes. You're assuming that the total volume is 2 liters. First thing, again, like we talked about with the other buffer situations, is ID the prominent parts of the equilibrium. So NH4 plus is essential to the equilibrium, as you see here, and NH3 is prominent in the equilibrium that you see here. Cl is a spectator ion that's not included. It's soluble, so it doesn't really matter in terms of the equilibrium. This makes a buffer, an equilibrium expression where NH3 and water put together. NH3 is a base. It's going to accept the hydrogen from it. It's a fairly strong in terms of a weak base. It accepts the hydrogen from the water to make ammonium plus hydroxide ion. We can take that and write that into a Kb expression, NH4 plus OH minus over NH3, and you would have to look up that Kb value from a chart or an appendix to figure out that value. It happens to be 1.8 times 10 to the minus fifth. When we use the Henderson-Hasselbalch equation, though, we don't use Kb's, we use Kas. So you guys know from the relationship that Ka times Kb is equal to 1 times 10 to the minus 14th. I've shown that down here in step 3. Those two multiplied together equal 1 times 10 to the minus 14th. So by dividing both sides by Kb, we get a Ka of 5.56 times 10 to the minus 10th, which tells you that the conjugate acid is not very strong, that the base is stronger than the conjugate acid. In the Henderson-Hasselbalch equation, we use pKa, so if you take the negative log of that, that becomes 9.25. So step 4, since NH3 is accepting the hydrogen from the water, that makes it a Bronsted-Lowry base, and its conjugate is NH4 1+. We're going to use those concentrations in order to figure out what we need in the Henderson-Hasselbalch equation. So down here on step 4, I show NH4 plus as the acid and the base is NH3. I'm not really worried about diluting anything at this point because it said that the total volume is the same, so we don't have to really worry about that in terms of the concentrations here. So Henderson-Hasselbalch pH is equal to pKa plus the log of the base concentration of the acid. Plug in the information I know. I know the pH of my buffer wanted to be 9. I knew that the pKa was 9.25 plus the log of the base concentration divided by the acid concentration. So I knew that the base was 0.10, and I didn't know the concentration of the acid in this case. Solving that in the Henderson-Hasselbalch, I went ahead and subtracted 9 minus 9.25 and got 0.25 on that side. To undo the log, I raised 10 to that power, so I raised 10 to the negative 0.25 power, and I got 0.56 equals 0.10 molar over x. Cross multiplying and then dividing both sides by 0.56, x became 0.18 molar. Here's where the 2 liters come in at. I need to know the moles of NH4Cl that I needed. So I took what I got from solving that as the 0.18 molar, I broke that into moles per liter and then multiplied by the liters of solution, because they told me in the original that the buffer volume was 2.0 liters. When I did that, I isolated it to be 0.36 moles of ammonium chloride. That's what I would have to measure out to get that buffer capacity. A couple things that are interesting: the closer your pH is to your pKa, the more effective the buffer is to neutralizing. Notice those are within 0.25 of each other. So that leads us to buffer capacity and pH range. Buffer capacity is the amount of acid or base that buffer can neutralize. Usually it's a range of pH values to effectively neutralize it, and the optimal range of a buffer is when the pKa equals pH. Usually the usable range of a buffer is plus or minus the pH value, one pH value. So it would be 7.0 if you look at 7.1 or 6.9. If we add a strong acid or a strong base to a buffer, we have to do two different steps to figure this out. Assume that the strong acid or base with the buffer does go to completion for neutralization, as long as you don't exceed the buffer capacity. As soon as you exceed the buffer capacity, all bets are off and you've exhausted its ability to neutralize the extra acid or base. We're going to use the calculated values of the acid and its conjugate, along with Ka, to find the hydronium ion concentration through an ice chart. And it's really not an ice chart so much as it is an ICF, initial change and final chart. And I'll show you that here in a second with the problem. So here on the back, this is a figure in your book, and it really shows the two-point process. You have the buffer, which is the weak base, the weak acid and its conjugate base. And if you add a base to it, the acid is going to react with the base, go to completion, neutralize it, and produce water and the conjugate base. If we add acid to it, acid plus the conjugate base is going to give you the weak acid, and it goes to completion. We have to do this through stoichiometry. Once you have it through stoichiometry, now you're going to use the equilibrium values to find out what the new pH is. And we're going to use the Henderson-Hasselbalch to try to figure that out. So here's a sample problem. A buffer is made by adding 0.3 moles of CH3COH, 0.3 moles of CH3CONA, sodium acetate to enough water to make 1.0 liters of solution. The pH of the buffer is 4.74. Calculate the pH of the solution after we add 5 milliliters of 4 molars NaOH. Step 1, let's identify what we have going on. We have a weak acid, CH3COH, and we have a weak base to the CH3COO. The Na is a spectator because it's soluble. This is similar to the common ion we talked about in section 1. So initially this is the definition of a buffer. I have some weak acid and I have some conjugate. So I need to figure out that equilibrium to begin with. And I converted it into moles because we're going to do stoichiometry and use molar ratios here in a little bit. It's convenient because they said we had 1 liter of solution, so we knew the moles already. Now what I'm going to do is I'm going to change the equilibrium by adding a strong base to this. And I need to know how many moles of strong base I'm adding because I need to do stoichiometry with the coefficients. So I converted 4 molar into 4 moles per 1 liter of NaOH multiplied by its volume in liters. So I had to convert 5 milliliters to liters. And I'm adding 0.020 moles of NaOH to the buffer. Well, in a buffer, when I add base, the acid is going to neutralize it and go to completion. So here's what I'm doing in step 3. I'm adding 0.020 moles of NaOH. I set up an ICF chart. Initial, change, and final. So hydroxide ion, I didn't have any at the beginning, but I had some weak base, I had the conjugate base, and I had the weak acid. When I add the 0.020 molar of NaOH into the solution, that's going to use up some of the acid because acid neutralizes base to make water and the conjugate base. Well, if I am adding the base here, that's going to make the conjugate base go up. So whatever that change is, the 0.020 moles, that's going to take away from the acid but add to the conjugate base. Now I'm just going to do what the operation shows me to do to get the final. 0.280 when I subtract and 0.320 moles when I get done. Again, we are assuming the OH is gone to completion, so we use it up completely. All right, so it's completely neutralizing this. Now it's not perfect because 0 plus 0.020 would be equal 0. I just want you to see that we'd have all the hydroxide ion used up. So now we need to find the new concentrations with a new total volume. So here's the acid, moles per 1.05 liters. Where did I get that from? I had 1 liter to start with, and I had 0.005 once I mixed them together for the new volume. So when I added the sodium hydroxide, I had to add its volume to it. You can't assume that it's negligible. So I solved for molarity, I got 0.279. And then whenever I took the moles of my conjugate base, 0.320 divided by 1.05, I got 0.318. To find the new pH, I used the Henderson-Hasselbalch equation. pH equals pKa plus the log of the base of the acid. So again, you're going to have to look up the Ka value of this weak acid, which is the acetic acid, that's 4.74, plus the log of the base concentration, which was the conjugate here, CH3COO, divided by the new concentration of the weak acid, 0.279. Plugging that into the Henderson-Hasselbalch, you get 4.796, which rounds to sig figs of 4.80. Now think about why that makes sense. I added a strong base, so that should make the pH go up. Now it doesn't make the pH jump up by a lot because we have acid and base to neutralize it. There's already some acid to get rid of it. So while it did raise the pH from 4.74 in the original solution up to 4.8, that wouldn't be as much as if we didn't have any buffer solution present. So those kind of walk you through the steps on how you can find out the effects of a strong acid or base on the buffer. If this were an acid, you would have the acid concentration H plus here that you added, and it would just be the base on this side you would use up, and you would increase your HA on the other side. Similar setup whether you're doing acid or base. I'll work through some more examples of these whenever I get back, and we talk about the finality of this in the video lecture.